In order for the ME-262 axial flow engine to suck in more air, all engineers had to do was to add more and more compressor discs. This meant a longer, more slender engine, far better suited for sleek airplanes. But in 1944, it had one big disadvantage.
Materials available in those days just did not withstand the stresses and the temperatures that these engines developed.
Jet engines are subject to incredibly high temperatures. In the ME-262, the finely engineered blades were particularly vulnerable. Its engines only lasted an average of 25 hours, even less if the fuel flow wasn't regulated properly by sensitive use of the throttle. Eric Brown was one of Britain's top test pilots. He was selected to fly captured German warplanes and report back what he found.
The first German jet I flew was the Parado 234s, the reconnaissance bomber twin jet. Same engines as ME-262. I taxied it out to the end of the runway, ran up the engines to full power, and was just about to release the brakes for takeoff when the starboard engine exploded, blew clean out of the airframe, taking most of the starboard wing with it.
In 1944, the metal alloys required to build a successful axial flow jet engine simply didn't exist. The materials of the day were not as advanced as the jet engine that needed them. Whittle was well aware of axial flow principles, but in 1930 he decided that it was too complex for the time. The fact that today this 60-year-old Meteor is still flying on its original engines stands testament to Whittle's engineering prowess. After the Second World War, the arrival of the jet had already started to change the warplane. But there is more to a successful warplane than the engine alone, and back in 1946 there was still a long way to go. On September the 27th, 1946, a dashing 36-year-old test pilot called Geoffrey de Havilland set out to make history. He was preparing to beat the world record of 616 miles per hour and become the fastest man on the planet. To do so, he would be flying close to the speed of sound. At sea level, this is 760 miles per hour. His aircraft, a prototype built by his father's company, the DH-108 Swallow. Geoffrey de Havilland took to the air, but at Mach 0.9, a whisker from history, the plane disintegrated over the Thames estuary. The death of such a competent pilot shocked everyone. In a desperate search to uncover the cause for the crash, engineers strengthened a second Swallow to follow de Havilland's flight plan. All they needed now was a pilot. There was only one man for the job, and it wasn't long before his world too began to shake apart.
You had an aeroplane going along and literally doing this. Almost a blur, it was oscillating so violently. With the G, I couldn't get my arms up to reach the blind and pull the blind to eject.
The instincts that kept Eric Brown alive in Germany kicked in again.
After 7 seconds of this, it stopped as quickly as it had begun.
Eric Brown had hit an invisible barrier and survived, and his was not an isolated experience.
All the leading nations of the world had very serious problems with high-performance fighter airplanes going out of control or beginning to go out of control as they flew faster and faster.
Little was known of the practical effects of high-speed flight. New wind tunnels were constructed to simulate wind speeds close to the speed of sound, speeds known as transonic. Using Schlieren photography in the new tunnels revealed high-pressure areas forming all over the aircraft.
This was the so-called compressibility crisis, or the beginnings of the whole problems involving the so-called sound barrier.
It was these shock waves at transonic speeds that were causing all the problems.
Transonic is a region of flight where you have supersonic flow over part of the aircraft and subsonic flow over part of the aircraft. It's a very difficult region to understand, even today, because you have this mix of flows between the two. Fully supersonic and fully subsonic are relatively easy to understand, but this transonic region becomes more difficult because of the different areas of the aircraft that are obeying different laws of aerodynamics. The way this is manifest to the pilot is that the shock wave moves back and forth very rapidly over the top of the wing, many times a second.
40 years of wing design needed rethinking.
Now, what I'm showing here is a typical wing about 12% thick, which means that that distance there is 12% of that distance. If you could, say, slim that down to 6%, the effects of the shock waves might be put off so you could go faster before you would get into these problems.
History was about to turn full circle. The early planes did have thin wings, designed to slice through the air. As aerodynamics became better understood, its thick wing could accommodate struts, wheels, and weapons. Clearly, there could be no going back. In pre-war World War II Germany, they discovered a simple and perfect solution. One that used a thick wing which appeared thin to the oncoming airflow.
So we now have exactly the same thickness there, but we've got a much longer distance, so it's relatively more slender.
This is no longer the straight wings, old-looking things with a jet engine slapped on. This is a real modern fighter as we think of it today as a jet fighter.
The F-86 Sabre looks like a modern jet warplane. And it was fast, but the Sabre still couldn't punch through the barrier. Close to the speed of sound, vibration and buffeting rendered the controls useless. It seemed like the barrier really was unbeatable. In October 1946, at Muroc Dry Lake in California, later to become Edwards Air Force Base, a top-secret research craft was making its first flight. But this wasn't a jet plane. It was small with straight, razor-thin wings, not swept. This was little more than a rocket-powered bullet. It was called the Bell X-1, and it had been built for one and one purpose only: to punch through the barrier.
The X-1 program, then called the XS-1 for Experimental Sonic 1, was a development program to try and develop a research supersonic aircraft capability.
With enough fuel for a 90-second powered flight, it was launched from a B-29 Superfortress. And yet, when the aircraft went to full power, it too failed. As the plane entered the transonic region, the Bell X-1 went into an uncontrollable dive. The control surfaces that pitched the craft, either up or down like any plane, weren't on the front wings, but on the rear ones. The focus was now on the tail. This is a model of the tail of the X-1. As the surfaces at the end of the tail move up or down, they affect pressure on the oncoming air and force the whole rig up or down, just like a real plane. As the wind tunnel powers up, the effect of the elevators on the rig can easily be seen. Crucially, these wind speeds are well below the transonic danger zone. When smoke is added, you can see the smooth airflow around the airfoil. But close to the speed of sound, shock waves on the front wings create turbulent air for anything in their wake. This means that the elevators on the tail are operating in dead air, rendering the controls useless.
So what happens is the airflow, instead of flowing smoothly back over the trailing edge of the wing, is that it separates, and you have this large dead wake caused by this shock wave. The problem is all the control surfaces are right there in this dead wake, and so you lose a bit of control authority when this happens. And so there's a very real danger of a pilot not having the fine control that they're used to having.
On the Bell X-1, that danger was putting the life of the pilot on the line. And the X-team weren't the only ones to know this. The British government had their own secret plan to be the first to look what lay beyond the sonic glass ceiling. And it involved none other than Frank Whittle. In 1943, 3 years before the X-1 got off the drawing board, the Miles Company had been commissioned by the British government to build what would be called the M52.
It was estimated that they would be able to achieve a Mach number of about 1.1, or something like 1,000 miles an hour.
And it was to be piloted by none other than Eric Brown.
I had been alerted by the director of the RAE that I would likely be the pilot to do the first flight in this and do the supersonic testing.
With the project nearing completion, there was suddenly devastating news. Frank Whittle, ignored by the government in 1929, shunned by the War Department in 1935, was now dropped by the powers that be and told to pack up. The project was cancelled.
Before the M52 was cancelled, we were instructed to give all the data to the Americans.
In the package sent to America was one technical innovation that would make all the difference: the tail.
In the flying tail, instead of having the moving bit, you make the whole tail solid, and then you move the whole tail, the solid tail.
The tail of the M52 didn't have small elevators controlling the pitch of the aircraft. Instead, the whole tail pivoted up or down. At the flick of a switch, the whole tail can present an angle up or down to the oncoming airstream.
There's a very big difference between just using the elevator on its own, where, it moved hardly at all up and down, whereas moving the whole tailplane, we get a very big difference.
The increased surface area of this new tail might make the difference in the turbulent transonic air. The British Miles team had been the first to realise the potential of the all-moving tail, and now the Americans came to the same conclusion, and the X-1 was modified. Now it was time to find out if it worked. On the 14th of October 1947, the Bell X-1 took to the skies again, but this time it had an all-moving tail. It was a memorable day, the day when Bell X-1 took Captain Chuck Yeager to the other side. After years of endeavour, the supersonic age arrived, not with a whimper, but with a sonic bang.
The rocket craft cracked the sonic barrier. Human flight, faster than sound.
At first, Yeager never even realised he'd done it. He thought his dial was faulty. Technology and human endeavour had done it. first jet fighter to benefit from the all-moving tail was the F-86 Sabre. With its all-moving tail, the Sabre could reach the speed of sound in a dive and the pilot remain in control.
To this day, this aircraft is still regarded as one of the most beautiful aircraft ever built, even compared to other jets. The lines on it are so smooth, so clean, so flowing. You look at it and it looks like it's going fast.
It was fast. The new jet fighters were capable of speeds their young pilots had never encountered, certainly not in combat. And that combat soon came in the Cold War in Korea in 1950. In the skies over Korea, jet engaged with jet in combat for the first time. American Sabre would be pitted against Russian MiG, axial flow jet against centrifugal. As a wartime ally, the Soviet Union had received centrifugal jet engine technology from Britain and created the MiG-15. The Sabre, on the other hand, was making use of the latest axial flow power plant, which gave the aircraft its more streamlined form.
These are the ailerons. The tail surfaces are hydraulic. The only thing that is not is the rudder, and that is still operated. The aircraft carries 6 M3 50 caliber machine guns, firing all 6 guns at the same time. You could feel the reduction of the aircraft slowing down because of that recoil in there that the whole aircraft was absorbing.
The Browning 50 caliber machine gun was fitted as standard on most American warplanes throughout World War II. The MiG was armed differently.
They carried 2 23mm rapid-fire cannons and 1 37mm slow-fire cannon. When the 23mm projectiles were going by my canopy, they looked like golf balls. And when the 37mm projectile was going by my canopy, it looked like a tennis ball. And you could hear them because they're supersonic, like that.
The bullets were supersonic, but the guns belonged to an earlier, slower age, as did their sights. Target opportunities in jet combat were gone in a flash.
In World War II, when they would look out, they would see fighters at a distance, but the jet fighter pilots had to learn to look at fighters a lot further out, so they had to see even better than before.
Firing bullets from a moving plane at a moving target was always difficult. At speeds in excess of 500 miles per hour,
gun battles,
it was becoming impossible.
Rotating aircraft, if the aircraft are turning around in any sort of way, then they might aim a gun in one direction, but in fact, it completely misses the target. So in order to compensate for the spinning motion, for the rotating motion, if I really do want to hit Ben with this ball, I have to throw the ball a bit to the left of Ben, like that, and there it goes, straight at him.
With the jet fighter, the problem, known as deflection, got a lot worse.
You have both a moving target and yourself are sitting in a moving platform, and then when you start thinking that through, you have the bullets that you're firing, which themselves are affected by gravity, affected by wind.
The jets didn't just have World War II guns. The MiG-15 had World War II gun sights as well, like this one from a Spitfire.
Now this is called a combining glass because it's combining the view of the outside world with this little graticule that's projected up through here. Now what we have on here are some means for presetting the range to the target aircraft. You also have another control that gives you an estimate of the distance away to the targets, and that really was the best you could do. The limitation is that you have no measure of the movement of the target.
And here was to be the significant advantage. The Sabre had radar ranging, capable of reading the distance to the target at any speed.
This is called a radome, It's a composite material. It's not metal skin like the fuselage. And behind this is the radar antenna. And it sent out a signal that would reflect off of a target, come back, be picked up by this antenna here, and then translated to an image up in the cockpit that would tell us whether an object was at 4,000 feet or 2,000 feet or 1,000 feet distance out.
It made the difference. Although the aircraft's performances were closely matched on paper, the domination of the skies by the Sabre became an overwhelming 10-1. The Sabre outgunned the MiG by superior targeting technology. In 1949, the Soviet Union detonated its first atomic device, and the arms race went nuclear. The world now had a nightmare scenario. Moscow and Washington within striking distance of each other, hordes of bombers armed with nuclear payloads. It was a real fear. Governments on all sides prepared for nuclear attack. Survival would depend on one thing: reaction time. A warplane was needed that was so fast it could destroy attackers before they could reach their targets, and both sides were investing in it. It was the supersonic interceptor.
We needed an airplane that was extremely fast, that could get supersonic speeds very, very quickly, because all it takes is one bomber getting through, because now they're carrying thermonuclear weapons. And one airplane literally could destroy an entire city. The stakes are very, very high.
The race was on for a supersonic intercept fighter, one that could reach Mach 1 and beyond in level flight. America's early response was the Convair F-102. The F-102 incorporated all the lessons learned in the assault on the sound barrier. It was designed to be the next generation of truly supersonic warplane. It ticked all the boxes, but it couldn't get there.
They have the big engine, they're using the swept wing, they're using the delta wing, which is nice and thin, it should be real fast, and it should go supersonic, but when they built one, guess what? It doesn't quite go supersonic.
Something was wrong. The sum of everything aviation scientists knew was there in the F-102. They had the jet engine, they had the latest wing, but they couldn't get through the wall. The demons were back. They turned to aerodynamicist Dr. Richard Whitcomb at NASA for help.
Almost all supersonic airplanes were not going supersonic because of this problem.
What was the problem?
The thing that they failed to understand at that time was the aerodynamics. They ended up with the thickest part of the fuselage being in the middle. And then the thickest part of the wings joined that fuselage in the same place. So if you took a series of cross-sectional cuts all through the aircraft, that you would find that the area would have this large jump and bulge in the middle.
But scientists had been here before. Schlieren photography showed all the clues. They had missed one.
Right near the speed of sound, there weren't shock waves for the fuselage and the various parts of the airplane. There was one major shock wave, one big shock wave for the total airplane. You remember, they all converged on one.
Whitcomb didn't look at the wing and fuselage as separate entities. He looked at them as one combined body and measured the increase in the cross-sectional area along that body.
He postulated that perhaps if you look in a more global sense of what the air had to do going around this vehicle, that if you made a Coke bottle shape, in other words, made the fuselage thinner where the wings got thicker and smoothed out the area over the curve, that you might reduce the drag.
Whitcomb proposed the fuselage should be sucked in where the wings connect to compensate for their additional volume. What the air sees is now a smoother increase and decrease in the volume of aircraft passing through it.
It was not the individual parts, but the total cross-sectional area that counted. And by indenting the fuselage, you improve it.
This principle became known as area rule. The F-102 was reshaped according to that principle. Changed the shape of the high-flying interceptor and thrust the warplane to speeds that would continue to mould it to the shape it has become today. The jet engine was a giant leap forward for the warplane, and now everything else has caught up. Swept wings, all-moving control surfaces, new materials, and digital avionics beneath its aluminium and composite skin. If there's one more chapter in the story of the jet, it's the metamorphosis of one warplane into another. The helicopter gunship. This is the very latest helicopter to join the US Marine Corps, the Cobra Zulu. At Patuxent River Naval Base in Maryland, they're developing and testing the latest rotary-winged warplanes. Like its fixed-wing siblings, the Cobra is bristling with the latest technology.
We're standing in front of AH-1Z, which is our newest Super Cobra. Now we have mission computers on this aircraft, the first time for the Cobra family. A huge leap to the 21st century since we designed these airplanes originally back in the 50s and 60s. The weapon system's all integrated on a mission grip, which looks a lot like your Atari or Xbox or PlayStation mission grip. So your kids are learning how to fly this helicopter today.
It was an idea that had been around since the sketches of Leonardo da Vinci in the 15th century. But the helicopter didn't fly until pioneers like Fokker in Germany and Ukrainian émigré Sikorsky in the USA put 20th century technology to work on a 500-year-old idea. This is Igor Sikorsky at the controls of his first test flight in 1939. By the Korean War in 1950, the helicopter had found a vital humanitarian role. The major issue in the Korean War was getting the injured out and back to field hospitals as quickly as possible. The helicopter proved a lifesaver. However, its large, heavy piston engine limited its potential.
Here we have a typical radial piston engine from the 40s, early 50s. Big, bulky, heavy, lots of things to go wrong with it. And then in the mid-50s, along came the turboshaft engine, far smaller, much lighter, much, much simpler, and twice, 3 times as much power.
In the helicopter, the jet engine doesn't use its power for thrust like in a jet plane. Instead, its power turns a shaft that drives the rotor blades, and it would transform the helicopter.
You could now carry more, you had more power, and also the engines were much simpler, so they were much more reliable.
A new generation of helicopter emerged. At the forefront was... As an air ambulance, it arrived in time for the Vietnam War.
Well, the Huey was originally designed for the air ambulance role, but it very quickly became apparent that it could do more than that.
The extra power, payload and reliability provided by the jet engine made the helicopter a versatile machine.
As good as this aircraft was at bringing wounded soldiers off the battlefield, maybe it would do just as good at putting them into the battlefield to begin with, and thus the idea of vertical envelopment came about.
Vertical envelopment meant dropping troops into hot landing zones. It was a dangerous job for the new air cavalry, and the Huey needed protection. Guns and rockets were fixed on the sides, and a gunship version was soon flying in convoy with the troop carriers.
The problem came that the Huey, which was carrying all the armament, was slower than the helicopter which was carrying the troops. And so that was why they decided to start looking at developing a particular attack helicopter, which would be faster, which would be more streamlined, which would just carry a gunner and a pilot. And that essentially was the birth of the attack helicopter.
That attack helicopter was the Cobra, and it's been in action ever since. Here at Lager in Germany, experienced pilots have been sent back to school to learn to fly their latest warplane.
Going to be double attack, 6K, and the fight's on.
Typhoon 1, wind is calm, you are cleared for takeoff. Typhoon 1, cleared takeoff.
These pilots will fly many hours on computer simulators before they're allowed anywhere near the cockpit of their new delivery, the Eurofighter.
This simulator in particular is used for cockpit familiarization, basic instrument flying, emergency procedures, and intercept procedures. We start out here to train the first Eurofighter pilots of the German Air Force, so it's not only a training for them to fly the aircraft, it's also a training for them to become familiar with the simulator, that they can train later on the students in the simulator.
After hundreds of simulated missions on the ground, the pilots are finally ready for their first flight. And so too is their new production warplane. After 10 years of meticulous testing, it finally joins its first active squadron here in Germany. The crew represents 1,000 hours of training, the warplane 100 years of technical evolution. And when the cockpit is closed, the two come together in unprecedented unison. The computer flies the plane, the man flies the mission. Technology never stands still. Its evolution is slow and incremental. But every so often, along comes a shockwave that changes everything. The jet created that shockwave. It redrafted the blueprint of the warplane and gave it the thrust to form a series of new shapes and fulfill a multitude of roles. The jet took the warplane from the 20th century to the 21st. No warplane and no war would ever be the same again. And be gone in a second. Not only is it fast, the Raptor is almost invisible to radar. They call that stealth. The man or woman who flies the Raptor must be at the peak of their profession. But the 100-year relationship between man and machine could soon be drawing to a close. Raptor is designed to fly, to think, and if necessary to attack, without human intervention. Where the warplane is going, soon man may not be able to follow. By the middle of the 20th century, technologies such as the jet and the rocket made global warfare a possibility. Tensions increased with the arrival of the Cold War. The threat of aerial attack had never been greater. Above the battle space today flies a communications hub, the Early Warning Aircraft, or AWACS. This eye in the sky uses its sensors to monitor air targets. Powerful onboard computers and their operators interpret the information. They can identify friend or foe and direct the might of the military to its target. The origins of the reconnaissance plane are the origins of the warplane itself. Right from the start, the airplane proved its worth to military commanders by becoming their eye in the sky. But on the vast battlefield of World War I, newly scarred with trenches and gun emplacements, the nimble little aircraft soon established another role, that of mapmaker.
If you go back to World War I, both sides do a lot of aerial photography. In fact, a lot of the air fighting in World War I is to prevent people from taking those photos.
The aerial photographer's ability to expose the enemy's defences gave rise to armed countermeasures. Air warfare had begun. The importance of the photographs was fully understood by the generals. Aerial intelligence had begun.
This is a World War I photograph, and I think at that time you can say that with the height limitations and with the target, and you were looking very much at the front line here, you were looking at something where the quality was adequate for the need. What the intelligence officer in those days was looking for was the structure of enemy trenches, the positions of barbed wire. Trenches were very obvious, beautifully castellated, and particularly with the Germans, very good soil disposal, so trenches stood out very well. We can trace the barbed wire on this photograph extremely well, and this is because the weeds and the grass under barbed wire are uncontrolled, and you do get quite a dark shadow from growth.
World War I proved the value of aerial reconnaissance. The need for high-definition pictures at greater speeds was met with the introduction of custom-built cameras.
The big difference between the end of World War I and World War II was the advent of the automatic camera. This was the F-24, which was typical of those early cameras. These would have been the best lenses available to the British at the time. Electric, motor drive, the whole thing is plugged into the aircraft electrics, and a simple switch in the cockpit gives you the ability to take 20, 30, 40, 50 frames.
But as the cameras got faster, so did the planes. In war, the reconnaissance plane needed to be always a little faster or a little higher than the enemy if it were to carry on doing its job unmolested. To this end, in 1939, the Supermarine Spitfire was stripped of its guns and armour and fitted instead with an F-24 camera. The mission to photograph beyond the German line. And it was all the vision of maverick Australian inventor and pilot, Sidney Cotton.
Sidney Cotton is perhaps the single most important figure in the creation of modern photo reconnaissance technology. He was one of the few to appreciate that reconnaissance could be taken beyond the confines of the battlefield.
Cotton rigged his plane with a secret camera. His plan was to covertly photograph German military installations. He didn't count on having to give a German general a free ride. Discovery would lead to certain death.
There is a story that Sidney Cotton actually undertook one of his missions with a senior German officer on board the plane, entirely unaware of what was happening below him.
And when he switched on the green light in the cockpit that said cameras running, the general said to him, "What does that do?" And he said, "Oh, that's my fuel state." Cotton was a man with almost no nerves, clearly.
On the eve of the Second World War, Sidney Cotton had invented the spy plane. Even as Sidney Cotton flew his covert sorties, his own superiors were testing a top-secret invention that would make all aircraft vulnerable. Radio direction finding was about to change the shape of war. In fact, radar, as it would be known, would change the shape of the warplane itself.
Radar is actually the first effective way of seeing without your eyes. You can actually find out where things are at considerable distances. Once you know exactly where they are, now you can talk about dealing with them.
The advent of radar had made wartime aerial reconnaissance more difficult. The end of the war saw the end of Sidney Cotton's missions. But his legacy, the spy plane, its time was yet to come. covert surveillance would come of age. One man would take the spy plane into the history books. His name, Clarence Kelly Johnson.
Kelly Johnson was just an unbridled genius. And you can just see in his daily journals how his mind worked and how he would take a design, a very advanced design, from the earliest stages to the final stages and always be ahead of the problem. He believed that he knew what was needed by the customer, and he would deliver it to them, sometimes even before the customer knew what they needed.
The new spy planes were designated U-2 for utility plane to hide their real job: surveillance for the CIA. By 1950, radar was powerful enough to see 10 miles high. Russian interceptors could only reach the same height. So Kelly Johnson designed a plane that could fly higher than both, 70,000 feet, nearly 13 miles high.
The U-2 was a remarkable concept in that it was very simple. It was basically a high-flying sailplane powered by a jet engine.
U-2's first flight was in 1955. A year later, it was approaching the Soviet Union on a highly secret mission to pull back the Iron Curtain and take a look.
This ability to see what the enemy is doing, to photograph what's going on in the Soviet Union so that you can actually discern on the ground what the facilities are doing, what the plants are doing, what nuclear facilities are, whether they're exploding atomic weapons. This ability, in a sense, to photograph the Earth and to see what's going on in your enemy's territories.
At last, the might of the secret Soviet armory could be counted. Flying and photographing 13 miles above the Earth, the U-2 enjoyed unparalleled access over foreign soil. But on May Day, 1960, its cover was blown sky high. Whilst on a secret CIA mission flying into Soviet airspace, U-2 pilot Gary Powers was shot down by a surface-to-air missile over the city of Sverdlovsk. The destroyed U-2 was paraded for the entire world to see. The radar-guided missile had caught up. Powers was put on trial. Sentenced to 10 years imprisonment for espionage, he would be repatriated 2 years later in 1962, in time to witness the U-2's finest hour. On the island of Cuba, photographs taken by U-2 uncovered a sinister threat: Soviet missiles within striking distance of the USA. The Cuban Missile Crisis brought global nuclear destruction closer than ever before. For 13 days, the world held its breath until the missiles were finally removed. U-2 continues its patrols today and has been active in 2 Gulf Wars. After the Powers shootdown, U-2 never again flew over the Soviet Union. The Iron Curtain slammed shut. The next biplane was already taking shape in the mind of Kelly Johnson, interviewed here in 1975.
We knew that in overflying Russia for 4 years that they were making important advances in radar and missiles. And so in 1958, 2 years before Gary Powers was shot down, we decided we'd try to make a follow-on airplane, which became finally the SR-71, to fly higher and 4 times as fast.
What Kelly Johnson proposed was a leap into the future. Only 10 years earlier, man had broken the sound barrier. Now Johnson wanted to produce a warplane that could go 3 times that speed. At 2,000 miles per hour, no missile would be fast enough to catch it. He called this one the SR-71 Blackbird.
If anyone had asked an ordinary designer to build an airplane with the requirements that were laid out for the SR-71 at that time, they would have said it's impossible.
Every part of this warplane demanded brand new technologies. Its skin wouldn't be aluminium like the U-2, but titanium to withstand the heat generated at super high speeds. A unique liquid was created to act as both lubricant and fuel. Its shape was like nothing that had gone before. Skunk Works engineers completely redrafted the warplane blueprint. But by far the biggest challenge was the engine.
The designers faced the problem of having an engine that would work all the way from takeoff at 0 speed up through Mach 3.
No jet engine existed that could take the Blackbird where Kelly Johnson wanted it to go.
Turbojets are good at the lower speeds, but for good fuel efficiency at higher speeds, you need a ramjet, where the air flows through the engine, is burned, and then goes out with the fewest obstructions possible.
In a conventional turbojet, air is squeezed into a combustion chamber by a series of compressors at the front of the engine, where it's ignited, creating thrust. Air entering a jet engine, travelling at twice the speed of sound, becomes compressed merely by the speed it enters the combustion chamber. The compressor discs of the turbojet become a hindrance to that fast-moving air.
In order to avoid putting both ramjets and turbojets separately in the same airplane and pay a big weight penalty, the genius of Pratt & Whitney was to add these bypass tubes around the core of the turbine.
At lower speeds, the turbojet engine is the power source, but at speeds over 1600 miles per hour, bypass tubes divert the incoming air, creating a ramjet. Everything about Blackbird was done in secret. At Beale Air Force Base, Kelly Johnson and the top Air Force brass turned out to witness the latest and greatest warplane to join the Strategic Reconnaissance Wing, the SR-71 Blackbird. Test pilot Jim Eastham was one of the first to see how far the Blackbird would take him, and there was no holding it back.
Well, just let this thing cook and we'll see where it goes.
It wasn't long before Jim was doing over Mach 2.
Gee, the next thing you know, this thing clicked up to about 2.3. So, maybe we're on to something. Just about the time we went back over our base, 3.0 showed up.
That day, Blackbird took Jim Eastham to Mach 3, over 2,000 miles per hour. Kelly Johnson's genius had lifted the Iron Curtain once again. Closer to Earth, the picture was very different. Caught in the standoff between the superpowers of the Cold War were many smaller nations, armed in turn by either East or West. Their wars were all too real. In the Arab-Israel conflict of 1973, the Russian-built radar-guided surface-to-air missile, or SAM, was developing a taste for low-flying warplanes, and the Israeli Air Force had no answer.
Over 19 days of conflict, the Israeli Air Force lost 109 airplanes, representing 35% of its pre-war combat aircraft strength. Quite clearly, had the war gone on for any extended length of time beyond that point, the Israeli Air Force might have been taken out of the conflict.
Israeli ground forces finally secured the victory, but their air force had been almost annihilated by the radar-guided missile. In the USA, the destruction of Israeli-piloted American warplanes, like this F-4 Phantom, came as a huge shock. Uncle Sam needed an answer to the SAM.
A very imaginative response was to attack the radar system itself, and do this by reducing the radar signature, the radar cross-section of the attacking airplanes.
If a warplane were invisible to radar, it would be invisible to missiles. It was a theory that would produce a remarkable result. This is stealth. The F-117 stealth fighter, the first warplane designed from scratch to be invisible to radar. How do you make a warplane invisible? By convincing the radar that it isn't there.
Radar is a sensor that uses microwaves to detect the presence of targets within its vicinity. By transmitting a signal into the space around it, the targets reflect echo signals back to the radar and therefore give away their presence.
Imagine this torch as the radar source and the metal as the warplane. Radar works like the beam from the torch hitting the metal. The light bouncing back represents the reflected radar signal.
Radar cross-section is the term used to describe the echoing area of a target. So in essence, the size of the target as perceived by the radar.
A microwave generator is used to provide radar energy. The amount of energy reflected back can be measured from different shaped objects which represent the warplane. The goal is to minimize that radar return.
Here we have a shaped target. We see that it has a rather large flat face. Now let's put this back in with the flat face facing directly towards the radar itself and see what we get. We can see now that there's a very large target response here that is recording a signal strength here of 24 milliunits.
To avoid a radar-guided missile, the warplane's signal would need to be almost zero. At Lockheed, fooling radar was second nature to their advanced technology division, known as the Skunk Works. U-2 they had designed to fly over it, Blackbird to outrun it. Now with stealth they proposed simply to deceive it. Kelly Johnson wasn't convinced, but he was no longer in charge. Instead, his hand-picked protege, Ben Rich, was running the show.
Ben Rich was an incredible character, a one-of-a-kind guy. He took over running the Skunk Works from Kelly Johnson in 1974. To most people in this country, and particularly in the U.S. Air Force, he is viewed as the father of stealth.
His former boss had been against the stealth program, but Ben Rich took a gamble.
Ben Rich was going really to stake his reputation, and indeed the reputation of Lockheed and the Skunk Works was a stealth program.
For the stealth program, Rich put together a team of specialists to work on the basics. The first break